Thank you very much for the introduction and for the invitation to give a talk in this seminar. Well, before we start, just let me mention that all the new results I will be discussing today are joint work with Alex Luque from Uppsala and my colleague Daniel Peralta-Salas from ICMAT. So today, let's see if this works. Today, the talk is about MHD, about magnetohydrodynamics. So let me start by recalling the equations. So MHD is a model of plasmas, and the way plasmas are modeled through the MHD system is by understanding the plasma as a conducting fluid, okay? So the way we're going to model the plasma is by taking the variables, the unknowns that describe a fluid, that's the density, the velocity, and the pressure. And also, since it is a conducting fluid and therefore it reacts to electromagnetic field, we also consider a magnetic field. Okay, so what do the equations look like? The first thing we're going to do is to assume that we have a homogeneous incompressible plasma. So that amounts to saying that the density is going to be constant. So we can set it equal to 1. And therefore, the mass continuity equation just means that the fluid is incompressible. So the divergence of the velocity is going to be equal to zero. This is the first equation here. To describe the evolution of the fluid, of the velocity, we take the Euler equation for an ideal fluid. And then that equation is going to read as the left-hand side here is just the acceleration, okay? And the acceleration is going to be equal to the gradient of the pressure that gives you a force. And additionally, we have to consider the electromagnetic force, right? We take the magnetic force, which is going to look like this. So we have the cross product of the current density, which is J, and the magnetic field. We are describing the plasma in terms of a magnetic field, but that doesn't mean that there's no electric field. Okay, what happens is that one can use Ohm's law to write the electric field this way. Okay, we assume that the plasma is perfectly conducting, therefore the conductivity constant is like plus infinity, and that gives us a closed expression for the electric field as the minus the cross product of the velocity and the magnetic field. To relate the electromagnetic fields, we use Maxwell's equations. So these are the equations we're going to see here. So the divergence of B is equal to 0, like there are no magnetic monopoles, if you want. And the evolution of the magnetic field is given in terms of the curl of the electric field. Okay. Right now, the only equation I have not described, or the only variable I have not described, is this current density, J, and that is given by Ampere's law. Okay, so we set J to be equal to the curl of B. And all these equations are a nice system of PDEs, quite complicated, but here we're lucky because we are interested in MHD equilibria. And that means that we're looking for stationary configurations of the plasma. So we set the velocity equal to 0. So in particular, we get rid of one of the vector valued unknowns. That's always nice. And additionally, the whole thing is going to be independent of time. So whenever there's a time derivative, we just get a 0. What do we get? A much easier system of equations, or at least shorter. Essentially, we have just two equations. On the one hand, as you can see, B cross the curl of B is going to be minus the gradient of the pressure. And additionally, we assume that the divergence of B of the magnetic field is equal to 0, okay? So those are the two equations we consider. The first thing we're gonna do in this talk is that we are not looking for solutions to this system in the whole space. We want to have solutions in a bounded domain, okay? Specifically, we want to have a toroidal domain. Okay, so a bounded domain space whose boundaries are torus. Why? Because these equations describe the behavior of plasma in magnetic confinement devices like tokamaks and stellarators, and are usually designed that way. Okay, so of course, since we take the equations in just a bounded domain, we have to consider some boundary conditions. The first condition we take is the usual one, that the magnetic field should be tangent to the domain. So say the magnetic lines will not leave the domain, they will stay inside. There's another condition that we will consider, and that's important because of the applications we want, and it is that the pressure should be constant on the boundary, okay? As you can see, the system is not only shorter, it's also probably more familiar, and there is good reason for that. because actually this is just, the first two equations we have are just the stationary Euler equation, okay, in 3 dimensions. To see this, just B is a magnetic field, but if we understand B as a velocity field of a fluid, and the plasma pressure is identified with the Bernoulli function, then it turns out that those two equations are just the usual 3D stationary Euler equations. Okay, that's why they're more familiar. What do we want to do with MHD equilibria? The question we have in mind is what can we say about the existence of MHD equilibria in general toroidal domains, okay? And furthermore, we are not looking just for an equilibria. We want equilibria such that the pressure is non-constant, and the level sets of that pressure are going to be like nested toroidal domains, or a nice foliation by toroidal surfaces, if you want, of the domain. Of course, if I just mentioned that we want to have solutions in a toroidal domain with a nice set of level sets, the first example that one has in mind, the best possible domain to consider this question, is of course the case of axisymmetric toroidal domains. Okay, what we can do then is that we can use the famous Grad-Shafranov ansatz, which essentially says that we should write the vector field B in terms of a string function, which depends on z and on the cylindrical coordinate. And thing is, with that ansatz, the Euler equation just reduces to a nice elliptic equation, which is called the Grad-Shafranov equation. Okay, this one here. And in there, h and f are unknown functions that we can pick at will. So since this is a nice elliptic equation, in particular, it's easy to construct MHD equilibria in axisymmetric toroidal domains. And in fact, we can also make sure that the level sets of the pressure are going to be nested tori of the kind we want. Okay, so there in the axisymmetric case, things really look peachy. In fact, this thing is so nice that we can do much harder stuff. Okay, I should mention a fantastic result of Gavrilov, who did something much harder. Okay, he used an ansatz like this to show that you can, in fact, construct solutions that are axisymmetric to the Euler equation in the whole space, in the whole R3, such that the support of those solutions are axisymmetric tori. All right, so that's much more than what we are looking for. Okay, the result is fantastic. The ideas are natural but very, very clever, but the paper is quite hard to read. These solutions were put in a broader perspective and analyzed further in a very, very nice paper by Konstantin Landwickel, which is much easier to read and which I certainly recommend. These solutions are the very best you can construct. All right, they're smooth. A wider but less regular class of compactly supported solutions, also with axial symmetry, was constructed in a later paper with Miguel Domínguez Vázquez, Daniel Peralta, and myself. I'd like to mention that because the idea of that construction is going to be useful here. Okay, what we did is that we constructed piecewise smooth solutions to the equations, and the way we did that is starting from solutions that live in an axisymmetric domain, extending them just by 0, and noticing that if a certain and trivial kind of a determined boundary condition holds for solutions to that equation, then actually we get weak solutions to the Euler equation in the whole space. Okay, so this is something we're going to use. What we would really love to know is the answer to Grad's conjecture. Grad's conjecture, which is relevant in plasma physics, was proposed like 50 years ago, and essentially it says that it's very hard to get solutions of the kind we want. That means with pressure constant on the boundary and level sets, pressure non-constant, and level sets that are toroidal nested surfaces. It's very hard to get solutions like that unless the domain is axisymmetric. So specifically, if we have a nice family of solutions like that, Grad conjectures that should mean the domain is axisymmetric, or these solutions are axisymmetric. This is, well, it is very natural. This is a beautiful question. And perhaps it is not just of academic interest, meaning that the picture we have here is a magnetic confinement device that was actually designed in Princeton some years ago. It's called a notatron. So as you can see, it's a confinement device where the toroidal domain is not axisymmetric. Well, actually, it's even knotted. Okay. Well, Grad's conjecture is wide open as far as I know. Nobody even knows, to my best knowledge, even if smooth equilibria with non-constant pressure exist in general non-axisymmetric toroidal domains. There are just a few results in this direction. One is a classical result of Lords, which says that if the toroidal domain we are looking at is not axisymmetric, but it has some symmetry, so it has a kind of reflection symmetry across a plane, then there do exist smooth equilibria with non-constant pressure. What you do is that you can use that symmetry to show that we have enough periodic trajectories so we can define the pressure as a function of the domain of those periodic trajectories, so to speak. Problem, of course, is that the pressure is not going to be constant on the boundary. The level sets are not going to be tori, but still it is non-trivial. A nice recent paper of Konstantin Drivas and Ginsberg says that what you can do is to construct solutions of this kind in domains that are not axisymmetric, but almost, provided that you are willing to add a kind of small external force in the picture. And the construction they have, which is very nice, is by considering essentially the same setting as for axisymmetric solutions, but in metrics that are different from the Euclidean one, different but similar. If you map those solutions in a non-Euclidean metric to the Euclidean case, that's a small error that you introduce in the equations. That is the smooth small force that appears in their construction. Okay, that's very nice. What we will do in this talk is to relax the irregularity assumptions. Okay, we would really love to know what happens with Grad's conjecture, but we don't know how to do that. Grad himself proposed that what you should be able to construct in non-axisymmetric domains are stepped pressure solutions. That means weak solutions to the equations for which the pressure is a sum of step functions. So it's constant. It takes different constant values in different regions in space. Okay, that is usually called the stepped pressure equilibrium, and that is true. And in fact, that was proved in a very nice, very influential paper by Bruno and Lawrence almost 30 years ago. What they did is that they showed that you can deform, you can consider like small perturbations of axisymmetric domains, and then construct stepped pressure equilibria for which the pressure is non-constant. Okay, it is not constant because there are jumps in the pressure. Just a small comment. Okay, the way we defined solutions like these, which are piecewise smooth, is well, that they're just weak solutions. We define them by integration by parts. Okay, the usual way. The relevance in physics of these solutions have been considered in several papers, and specifically, perhaps due to Grad's ideas, there's quite a number of authors like Hudson, Dewar, Hole, and others that have carried out numerical studies of stepped pressure MHD equilibria in domains that are far from axial symmetry. Okay, and that is what we would like to address in this talk. To do that, to try to construct these stepped pressure equilibria, we're going to use as building blocks Beltrami fields, which is my favorite class of vector fields, probably. Okay, a Beltrami field in a certain domain is a vector field that satisfies this PDE. Okay, so the curl of the vector field is proportional to the vector field itself, and the proportionality constant is usually assumed to be non-zero. Additionally, since we are interested in configurations where the fluid or the magnetic field stays inside the domain, we will assume that the field is tangent to the boundary of that domain. Okay. In particular, notice that if lambda is non-zero, the divergence of U is equal to 0. Just take the diff on both sides of the equation, right? The first thing I want you to notice is that we have a lot of Beltrami fields to play with. Okay, and that is an important observation. An obvious kind of solution, which is a sort of degenerate Beltrami field, is the harmonic field. of a toroidal domain. By Hodge theory, you know, there's just one harmonic field in a toroidal domain. It's unique up to a multiplicative constant. And that is a kind of Beltrami field for us. More Beltrami fields are obtained if you notice that the curl operator is actually self-adjoint in a dense domain in this space, okay, the space of L2 fields that are divergence-free in the sense of distributions or whatever, and L2 orthogonal to the harmonic field. Okay, in that space, curl is self-adjoint, so you get actually an orthonormal basis of this space, which consists of Beltrami fields. So that's a lot of Beltrami fields. And furthermore, if you take some lambda, which is not in the spectrum of the curl operator and which is non-zero, then you get a unique solution to this boundary problem here, which says that you take the Beltrami field equation with that constant, essentially any, you assume the tangency condition on the boundary, and you impose that the L2 product between the solution and the harmonic field is non-zero, so you normalize it to 1. That gives you yet another Beltrami field. So as you can see, we have many, okay? These fields are all nice. In particular, there are solutions to a Helmholtz equation of this kind, so obviously they're smooth. For the purposes of this talk, we need to know that, in fact, if the domain is analytic, actually these Beltrami fields are going to be analytic up to the boundary. Okay, that is true. The best way I know to prove it is that well, the curl operator is not elliptic, but you can take this boundary value problem and you can reformulate it as a sort of another boundary value problem, which is a regular one for an elliptic operator. Which elliptic operator? Which is a kind of Dirac operator. So the square is essentially like the Laplacian. And it is a bit messy to define because we have to, because it acts on the space of differential forms of mixed degree. So any differential forms, they get together. But I believe this is the most efficient way to prove that things are analytic up to the boundary. So now that we know we're going to be playing with Beltrami fields, I can state the main theorem, which says that we have stepped pressure equilibria with non-constant pressure in generic toroidal domains. Okay, so the way we do it is that we start with a certain toroidal domain. Let's call it omega 1. We pick a Beltrami field in this domain. There are many. We pick just one. Let's call it V1, and assume that this Beltrami field you have picked satisfies certain non-degeneracy conditions, which are very mild, but which I'm not going to state here. Okay, we'll get back to that later. Then what we can do is that we can construct a collection of nested toroidal domains, omega 1 contained in omega 2, contained in omega 3, all the way to omega n for any n we want. So these domains are essentially like small thickenings of the original domain we had. And what do we do with that collection of domains which are analytic, all of them diffeomorphic and whatever? Well, what we claim is that if we take the larger domain, which we are calling omega n, there we have a piecewise smooth MHD equilibrium. What does the equilibrium look like? Well, in the gap between consecutive nested toroidal domains, that's a Beltrami field. So it satisfies the Beltrami field equation with certain constants that can be chosen freely. The pressure is constant between different toroidal domains. And of course, if we go to the innermost toroidal domain, the original domain omega 1, there the magnetic field is just the Beltrami field B1 that we started with, okay? And of course, we can pick the constants so that the pressure is equal to 0 on the boundary, okay? So that's how we construct these equilibria. What's the idea for this construction, okay? The starting point is that, as you have seen, we are using Beltrami fields as building blocks to construct more complicated solutions. So the starting point is a technical lemma that allows us to patch Beltrami fields together to get an equilibrium, okay? Let me take just the case of two domains, okay, omega 1 and omega 2. The idea is that if we take two domains, omega 1 contained in omega 2, we don't care about topology, we don't care about anything. Suppose that we have a Beltrami field B1 in the first domain and another Beltrami field B2 in omega 2 minus omega 1, so in the gap between those two domains, okay? And suppose that the Beltrami fields are tangent to the separating surfaces, okay? Then what we prove is that if we take this difference, okay, so the difference between the square pointwise norm of the Beltrami fields, if that difference is constant on the common surface, on the common separating surface, which is a torus, then we can construct an equilibrium. And the way we do it is just by piecing them together. Okay, so the weak solution is just B1 in the innermost domain in omega 1 and B2 in the difference between omega 2 and omega 1, so in the region that separates both toroidal domains. And the pressure is constant in each piece. We can write down a formula. Okay. So that is the starting idea of the proof. How to prove this result? Well, this is just the assertion that this explicit field is, and this explicit pressure is a weak solution to the system. So we just integrate by parts. Everything is nice and smooth inside the toroidal domain. So you just take smooth functions there. You integrate to your heart's desire, and that's it. Nothing more sophisticated than that. Okay. So this lemma is very straightforward, but it gives us an idea about the kind of strategy that we can use. Okay, so the idea is that we're going to start with a certain Beltrami field in a toroidal domain omega 1, so let's call it B1, and then we want to construct another Beltrami field B2, like in a small thickening of the toroidal domain we started with. Okay. There are two conditions we need for that new Beltrami field B2 so that we can patch these two Beltramis to get an MHD equilibrium. The first condition is that if we look at the difference between the pointwise norms, the square of the pointwise norms of those Beltrami fields, that has to be constant on the boundary of the initial domain, okay? For that, we have to be able to construct, of course, many Beltrami fields. There are many, but we have to be able to construct them efficiently. And the tool we will use for that is a kind of Cauchy-Kovalevskaya theorem for Beltrami fields. Okay. Of course, that's not enough. We have to ensure that in the second Beltrami field, we can find like a larger toroidal domain such that this second Beltrami field is tangent to it. To put it differently, we know that this Beltrami field B2 is going to be tangent to the initial one. That will be a sort of initial condition, but we need another torus to which this is tangent. Toroidal surfaces to which a vector field is tangent to are just invariant tori, so that means we are looking for invariant tori of this Beltrami field B2. And we have a tool for that. That's called KM theory. Okay, so that's the second tool we will need, a kind of KM theory for divergence-free fields. And that gives you a slightly larger toroidal domain that we have constructed by enlarging omega 1. If you want to have not just one layer, but many layers, just rinse and repeat. Do that as many times as you wish. And that's the proof of the theorem. So the first tool we have is, the first tool we need to use is that KM theory for divergence-free fields, for divergence-free fields, okay? So the setting is that we suppose that we have constructed that Beltrami field B2. It is tangent to the boundary of the first toroidal domain. So that is an invariant torus. We need more invariant tori. So we can use those Beltramis, those toroidal domains to enlarge the domain and to construct a weak solution, okay? In principle, we are not scared by that because a typical KM result is that if we have, if a vector field which is divergence-free and whatever in 3 dimensions, has a certain invariant torus, and some conditions are satisfied, and you expect them to hold, then that invariant torus is going to be accumulated by more invariant tori. We just pick one, we use it to define a larger domain, and that's it, Bob's your uncle. The problem here is that this is a typical KM result, but we can't prove it with a typical KM theorem, okay? The reason is that if you go to the KM theorems that we have for 3-dimensional divergence-free fields, all those theorems assume that either the field is close to being integrable, or they use the trajectories of the vector field to reduce the analysis to that of its Poincaré sections, which is a two-dimensional array-preserving map. Okay, and there you can use the twist theorem of Moser. But this is not going to work here. And the reason is that since we are interested in what happens to Beltrami fields in very complicated toroidal domains, so we are very far from the axisymmetric case, we have no idea what the trajectories of the vector field are going to look like. No idea whatsoever. Okay, we don't know how to go around this. So our first objective here is to be able to have a kind of KM theorem that we can apply in this setting of three-dimensional divergence-free fields that does not require us to know things about the trajectories of the vector field, okay? Specifically, what we want is to have a non-degeneracy condition, a twist condition, that only involves essentially local information, okay? So that is the first thing we have to prove. To do that, there are two ingredients that we need to use. One is obvious, okay? Because it's an ingredient that is always needed in a KM argument. We need the vector field, which in this case will be B2, to satisfy a certain Diophantine condition on the invariance on the torus given by the boundary of the first initial domain. Okay. By that we mean that we can linearize the vector field, so we can pick global coordinates on the boundary of the domain omega-1, such that the vector field in those coordinates is a linear flow. Okay, so omega-1 and omega-2 are just constants, and those constants are Diophantine in that if you take the dot product of that constant vector with an integer vector, a vector with integer components, that's non-zero, and actually it's bounded away from zero, okay? And we are very okay with a hypothesis of this kind, because actually the set of, as you know, the set of Diophantine vectors has full measure, so that's fine. The ingredient that is not obvious is that we want to find a twist condition, a non-degeneracy condition, that does not involve integrating over trajectories. We just want it to be written in terms of the strain rate tensor of the vector field. Okay, something we can compute with the equation. And it turns out that if we consider averages of this explicit vector field, whatever that means, we don't care about the meaning of this, everything works fine. And that gives you an explicit twist condition for the torus, which is actually the most important part of the argument, okay? So we don't care about the details. We just want to know a particular application of this KM theorem, which says that if we have a vector field, which will be B2 in our case, which is divergence-free, analytic, and which has an invariant torus satisfying a Diophantine condition, and that explicit twist condition is satisfied, then we have a lot of invariant tori that accumulate on the initial one. And that allows us to define the toroidal domains that will be needed to construct the weak solution, okay? The proof uses ideas of De La Llave, González, Jorba, Villanueva. Thanks to these authors, constructing the iterations is not so hard. What is interesting here is to actually come up with the idea that there's a twist condition that you can define using just the vector field without integration, without complicated stuff. When you have the formula for that, you see that actually this is perfectly well suited to the kind of PD that we have in this problem, and we can show that everything is going to work smoothly, right? I'm going to skip the details here. Let's see how we can construct the vector field V2 to which we want to apply this KM argument, okay? I told you we have lots of Beltrami fields, and that the tool that we're going to use to choose the one we want is going to be a Cauchy-Kovalevskaya theorem, okay? That's not new. That was, Danny and I proved it like 10 years ago. So this is, in principle, this is known and easy, okay? The idea is that if we take some analytic surface, which in this case is going to be the boundary of the first domain of omega-1, and we take an analytic vector field that is tangent to that surface, we can assume it just lives on the surface or that it is defined away from the surface. We don't care. It turns out that the Cauchy problem given by Beltrami fields, so solutions to the Beltrami field equation that are equal to that tangent vector field on the analytic surface, it turns out that this problem has a solution if and only if a certain constraint equation holds, okay? And this constraint equation just means that if we look at the vector field that we are prescribing, we look at that from the point of view of the torus that we have, okay, from the surface. We take the dual one form on the surface associated with that Cauchy datum, then that one form has to be closed. So the exterior differential of that guy has to be 0. If that form is closed, there is a solution, otherwise there is not. The basic idea here is that the curl operator doesn't have any non-characteristic surfaces, so you expect that an application of Cauchy-Kovalevskaya should be hard. The meaning of this constraint equation is actually very easy, okay? Just to get some intuition, assume that the surface that we start with is just a hyperplane, just a plane, okay? So x3 equal to 0. Then the constraint equation just means that the third component of the curl of B has to vanish on that plane, okay? And the idea, of course, is that the third component of curl by the equation is just going to be lambda times B3 times the third component of the field. If you want this vector field to be tangent, that means that this guy is going to be equal to 0. So of course, then the third component of B also has to vanish if there's a hope we can solve the problem, okay? So the constraint is obvious. What is non-trivial is that if the obvious constraint is satisfied, then we do have a solution, okay? But that is what we will use. And now we see how the proof is going to go, okay? Our goal is then to construct analytic vector fields that are tangent to our toroidal surface, to the boundary of the toroidal domain omega 1, to which we can apply this Cauchy-Kovalevskaya theorem to construct MHD equilibria. So what do we know? What do we want specifically? Well, we have the boundary of the domain. We want to construct an analytic vector field which is tangent to this domain, and such that the constraint equation that we need to apply Cauchy-Kovalevskaya holds. So that associated one form has to be closed. And also we want to construct MHD equilibria. So that difference of the square norms between this guy and the original vector field V1 that we had, that difference has to be constant on the surface, okay? So our goal is to construct a tangent vector field X satisfying that condition. How can we make our life easier here? Well, the first observation is actually very silly, but it is very useful, okay? We are thinking about matching conditions with this B1. Thing is that the argument I gave you about why that constraint equation has to hold, well, that works both ways. So in particular, as B1 is a Beltrami field, if we take the dual one form associated with that Beltrami field B1, that is going to be closed, okay, necessarily. So that is good. And also, eventually, we will want to use the KM argument applied to that result. So we're going to need a kind of Diophantine condition. We can start using it now. So we can make the assumption that actually B1 on the surface, on the torus, is going to be Diophantine. So we can pick global coordinates phi, so that y is just this vector field, okay, with omega being a Diophantine condition. Once we know we have all those things, the most efficient way, I think, to define this analytic vector field is to say that on the torus, the vector field is just going to be B1, which is y, multiplied by a constant, because that is convenient. And then to that closed vector field, we're going to add these guys, okay? We're going to add the gradient of a function, h, that lives on the toroidal surface, and the gradients of the coordinates, okay? Multiplied by constants a1 and a2. So that is how we're going to construct the vector fields. And the freedom we have are just those three numbers, C, A1, and A2, and a function that lives on the toroidal surface, okay? And what is great is that since we know that this Y satisfies the condition, and this is just a constant, then automatically the Koshykoff-Levskaya constraint that the associated one form has to be constant, has to be closed, is just going to hold, okay? Of course, the gradient here is not so, is a bit messy because it's used using the metric on the surface, the first fundamental form, but whatever, this is how it goes, okay? So now, what we know, the Koshykoff-Levskaya constraint is satisfied by an equation of this form. Now we want to show that the second condition we had to be able to construct MHD equilibria is going to hold. So the difference between the norm square of this guy and that of the initial Beltrami field we had, which is called Y, that guy has to be constant. We have added some additional constants here and there that don't play any role in the argument. Okay, this is just because it's easier to keep track of things here. And the result is that actually you can do that. Okay, you can construct X of this form by choosing H and the constants so that this MHD equilibrium condition holds. Okay, and everything is, and we can do that as long as C is not too large, and everything is going to depend nicely on C. Okay. If you look at the theorem, there's another condition that we are imposing, and we are imposing that just like Y was conjugate to a linear flow with a Diophantine condition, the same is going to be true in the case of X, in the case of the new vector field. Okay, the frequency vector is a little bit different. Okay, but it is explicit, and it has exactly the same Diophantine constants. Okay. Why are we doing that? Let's see if we can explain. The first thing we should notice is that if we go to the equation we want to solve, which is this this condition that we had to get an equilibrium, thing is, if you write that in terms of your unknowns, which are this scalar function and some constants, what you get is a Hamilton-Jacobi equation for H, essentially. Okay, and this is the equation we have written here. In general, if you have a Hamilton-Jacobi equation, the first idea we had was to use trajectories to solve the problem. In fact, if you go to the paper by Bruno and Lawrence, analyzing trajectories when you are close to the axisymmetric case is one of the key facts, one of the key difficulties that you have to tackle. Okay. Unfortunately, we don't know how to do that, and this is because since we are far from the axial symmetry, we don't really know what the trajectories are going to look like. All right, that's not how we solve the problem. Instead, the idea we use here, or the way we want to understand the equation, is we want to isolate this first part of the equation, and we understand this as a perturbation of this linear equation. Okay, L of omega of the unknown function H on the torus equal to something. Okay, equal to stuff. And L omega just means that you take the derivative of the function H in the direction of the constant vector omega. In principle, this is not so bad, okay? Since omega is Diophantine, as long as this stuff here on the right-hand side has zero mean, and that's something we can ensure by picking the constants in a suitable way, in particular using the constant B, as long as that has zero mean, we have a unique solution, and it satisfies nice bounds because the frequency is Diophantine. So this way, we know we can do something. So how does the proof go? We want to set an iteration, okay? We start with that first order approximation to the solution. Now we go to second order. And again, we isolate that second order contribution. We get something else on the right-hand side. We can ensure there's no mean, and eventually we want to solve an equation of the form L omega plus small error of the unknown function equal to stuff. The problem here is that one cannot solve this equation, all right? That equation can be solved as long as the frequency satisfies a Diophantine condition. if there's a small error, we cannot guarantee that omega is going to be Diophantine. In principle, it will not. And then it isn't just a technical thing that the errors, the estimates become a little bit worse. Simply, we cannot solve that equation. Okay, that just doesn't work. So the key idea of the proof is to notice that that is the essential difficulty for solving the equation. Okay. So what we do is that we enlarge the system. Okay. In addition to the variables we have, we're going to consider an unknown diffeomorphism, and that diffeomorphism is going to be written like this. It is the identity plus V, V being another unknown. And to the original equation we had, which I had just written down, which is just the condition to be able to construct an MHD equilibrium, we add yet another equation, okay? We say that if we take the vector field X that we had, which was written that way, we pull it back with that diffeomorphism, so with that change of coordinates, in those transformed coordinates, what we see is, again, a vector field with a Diophantine frequency. And we just massage the constants so that things more or less match, okay? We could have done differently, but this prescription works. So that is the key idea of the proof. As long as we have that, we will be able to iterate, and we will eventually get a solution. How are we going to set the scheme? Well, since we want to apply Cauchy-Kovalevskaya, we want analytic functions, so we will use analytic norms, which are defined in the usual way. And as I mentioned, as long as the frequency is Diophantine, we are going to have nice estimates. In this case, we are borrowing the Roosman estimates, which says that depending only on the Diophantine constants that we have, we can estimate solutions to the equation in terms of analytic norms. Okay, we have to lose a little bit of analyticity here, but everything happens in a controlled way, and that is going to give us a set of very nice estimates. Okay, why does this Diophantine condition appear here? Well, just notice that if we apply the inverse of that operator to a guy of this kind, where we assume that the zero term does not appear here because we have zero mean, well, that just means dividing by this Fourier multiplier. As long as this is bounded away from zero, we will get nice bounds. That's the philosophy. Okay. So that is how we approach the problem. Well, the dilemma we prove essentially is that if we take the constraint equation we wanted to solve, we append this second equation. So we enlarge the system to get another equation. And we assume that we start with an approximate solution that is nice enough as long as a certain non-degeneracy condition is satisfied, then we will be able to construct an actual bona fide solution, okay, to the problem. And that non-degeneracy condition reads like this. It means that we have to construct matrices that involve the diffeomorphism that we start with and the initial functions, so the approximate solutions and stuff like that. Then we take the average of those functions over those matrix valued functions over the torus. We take the determinant, and that has to be non-zero. So we have to be able to invert that matrix, okay? And this is where the non-degeneracy condition I told you about is going to come from, okay? From being able to invert the different functions that appear here and there. Of course, we are using here analytic norms because we want to use Cauchy-Kovalevskaya. You can prove essentially the same result in Euler or Sobolev spaces. What does the non-degeneracy condition look like? Something like this, okay? The matrix whose average you have to compute is going to look like this, essentially. And here, as you can see, we are just writing everything in terms of a matrix G, which is just the metric on the toroidal domain, so the first fundamental form. The frequency, omega 1 and omega 2, that's the Diophantine condition we have. And then a function R, which is a solution to an equation of this form. Okay, this should be the same R as above. Okay, I'm sorry. So as you can see, this is something that is completely explicit. That is why we can, or reasonably explicit at least. Of course, the question here would be, okay, this is explicit, but is this condition satisfied generically or not? We can do that. I mean, we can construct this matrix using any Beltrami field on any toroidal domain. You have uncountably many. You just want the determinant of a certain constant matrix to be non-zero. So everything is shouting, yeah, that is going to hold generically. But truth be told, we have no idea. The problem is that with these non-generic or things that you certainly expect that to hold generically, okay? But proving that those vector valued or matrix valued conditions hold in a generic sense is typically very hard, even in contexts that in principle are expected to be simpler, like spectral theory. It is usually very hard to show. Again, we have no idea how to show that actually this is satisfied in general. We would bet that, of course, it is going to be satisfied, but how to prove that? At least what is great is that in cases where we can analyze the problem a little bit better, and that case is that of thin toroidal domains, you can prove it. And actually, essentially anything that you use is going to work. You can even take the harmonic field in a toroidal domain, in a thin toroidal domain. So you take any curve in space, any curve you want, you thicken it a little bit, you compute the harmonic field in there, and generically, the condition is going to solve. You don't have to do anything else. In general, probably it will hold, but how to prove it? No idea. But the thing is that with that, the proof of the result I mentioned is done. Okay. There is another problem you can take as well if you want. Okay. That is sometimes called a free boundary problem with an external current. Okay, and it is quite similar to the one I mentioned before, but instead of looking for MHD equilibrium on a certain bounded domain, you look for solutions in the whole space. Okay, this is different. Okay, so you take the same system of equations inside the domain, and then outside the domain, you say that there's a sort of external magnetic field, which is generated by an external current that is a current sheet, meaning that it is of this form. Okay, it just lives on the surface of a certain toroidal domain, which is larger than omega, than the one that we are looking at. Okay, and then you impose some boundary conditions, some tangency conditions, and whatever. You will also find that the difference between the norms of those two magnetic fields have to be constant. Actually, this constant is going to be equal to 0 here, so things are continuous. And this is to define a solution. Okay, and that is how you define that free boundary problem. Okay, and this describes certain kinds of plasma confining devices. Another unknown, of course, is this omega prime that we have to be able to construct as well. So it is natural to wonder if we can do the same thing in this case. In this, we don't really care about the details so much, okay? But can we do the same in a free boundary problem? It turns out that you can, and that actually it is a bit easier, okay? So the idea is the same. We start with a certain toroidal domain. We start with a Beltrami field in that toroidal domain, and we assume that a certain non-degeneracy condition is going to hold. I'm not going to write it down. It is not the same one we had before. It is another. But again, I have no idea if that holds in general, but probably it does, but I don't know how to prove that. If you go to the case of thin toroidal domains, it is satisfied generically, just like before, okay? Even in the easiest case of just harmonic fields. Then what we can show is that you can take another toroidal domain and a current sheet, so a current a singular current density that lives on the boundary of that domain, which generates an external magnetic field for which the equation holds. Okay, just a few ideas about how to prove that, to see that it is very closely related to what I mentioned before. We start from a Beltrami field, just as before, and to construct. And what we do is that, again, we're going to use Cauchy-Kovalevskaya. But what we want to do with that, with Cauchy-Kovalevskaya, is to construct a harmonic field. It is not going to be defined in the whole space. Cauchy-Kovalevskaya doesn't give you that, okay? But it is going to be okay in a neighborhood of the first toroidal domain. The Cauchy datum that we take is just the initial Beltrami field. So here things are easier because we don't have to solve a Hamilton-Jacobi equation. We just take the initial Beltrami field that we started with, nothing more, okay? Then conditions are satisfied, and it turns out that we have everything is going to work fine. We just have to ensure that a certain twist condition for the KM argument is going to hold, but we know how to write that. We can't play with constants as we did before, but we don't care. We get something explicit, and that is the non-degeneracy condition that we mentioned, okay? Since we assume that twist condition is going to hold, then again, the boundary of the initial toroidal domain is accumulated by invariant tori. We pick one of those. We use them to define the surface of the new toroidal domain omega prime, and then you just take the harmonic field and cut it off. You set it equal to 0 outside that domain. That gives you the current sheet, and that's it. So just as before, but you don't have to fight with the Hamilton-Jacobi equation. We can actually, you can get explicit formulas for the external current, for the magnetic field, stuff like that, but we don't care that much about the details. Since it's getting late, I'm going to stop here. Thank you very much for your attention.